All right, let's get started. As always, if you have the homework that's due today, you should turn it in. If you don't, you should get it done.
How are you, sweaty? Wendy?
I'm doing all right. Okay. So we are going to continue moving through chapter 12. And last time we were talking about the intermolecular forces, okay? The things that basically hold liquids and solids together. If you remember from the kinetic molecular theory, it says that gases, those particles, really don't have any interactions. Okay? So everything that we were talking about last time has to do with liquids and solids. Liquids and solids. Which works out because section 3 that we're going to talk about today is titled Liquids and Solids. Okay. Now, the kinetic molecular theory, it was designed to explain the gas behavior, but it still works for liquids and solids. Okay, now we have to change a couple of the assumptions. Obviously, there is interactions between these things. And, you know, obviously that makes a difference. But other than that, you know, being the other things still pretty much hold up. Anyway. Okay. Now we already know that liquids will take the shape of their container. Right? Pour liquid in here, it takes the shape of the container. If we were to pour that into a different container, it would take a different shape. That is also true of gases. Remember, it's possible to pour gases. Okay, they take the shape of whatever they are in. The difference is gases will expand to fill their container. Gases don't sit and pool at the bottom of the container so much. They expand to fill. That obviously is not the case with liquids. Okay? All that liquid is sitting down there at the bottom. It has what we call a fixed volume. So this water that's in there has a specific volume. If we were to pour it into a different container, it would take a different shape, but it would have the same volume. Okay? No matter what container you move it to, it's going to have the same volume. And that's because we have this interaction between the particles, which keeps them closely attached to each other, sort of. So. All right. The next thing that we want to talk about, density. Well, obviously, liquids and solids are more dense than gases, right? Gases, we know, have all of these particles moving around and they're far apart. Liquids and solids, a lot more particles. You can also just Your experience will tell you that. Okay, if you have an empty water bottle, now it's not truly empty because there is gas in there. There's air. Okay, so there is something in there. But if you compare the mass of an empty water bottle to the mass of a full water bottle, they're very different. Okay? The reason for that is density. Remember, density is mass over volume. Okay? The volume of the water bottle hasn't changed, but the mass has gotten bigger. So if you have the same number that you're dividing by, you take the numerator and make it bigger, that also gets bigger. Okay? If that doesn't make sense, think of it this way. You have 4 divided by 2, that gives you 2. But if we raise the mass, let's say to 6, but keep the volume at 2, that changes to 3. Okay? It increases the density. Okay? So liquids and solids are much more dense. Okay? As a result, liquids don't compress. Okay? If you take a gas in a container and you put more and more of that gas in it, you force those particles closer together. Okay, that makes sense, right? It's the same container, but you're putting more things in it, they have to be closer together. Now, eventually, if you put enough of it into that container, the molecules get so close that they become a liquid. You have compressed it. You've taken the molecules and squeezed them together so that they get closer together. What happens if you try and squeeze a liquid? Can you compress it? Can you make those molecules go closer together? No, you can't really. I mean, if you want to be technical, yes, you can just a tiny bit, but it's such a small amount that you don't notice it. Okay? And it requires massive amounts of pressure. So pretty much we consider liquids to not be compressible, okay? Because under normal circumstances, they aren't. Moving on, fluidity. A fluid. Now, as we said, gases and liquids are both considered fluids. So what does it mean to be a fluid? Anyone? What do you think of when you hear fluid? Okay. Fluids do mix very easily. That's half of it. The other half is they flow. You can pour them. Okay? You can pour them. Now, because there's more interaction between the molecules, it changes it from with the gas. Now remember, the gas we could pour very easily, and you know it just moved. Okay? Liquids sometimes they pour very easily, but sometimes they don't. Can anyone think of a liquid that doesn't pour very easily? syrup, okay, ketchup, okay. Ketchup is a little bit interesting because it sort of acts non-Newtonian.
What? Huh?
Non-Newtonian. If you subject non-Newtonian fluids to fast, strong compression, they act solid instead of liquid.
Oh.
If you've ever heard of oobleck, you know what oobleck is?
Yeah.
You mix cornstarch and water,
Oh.
and then you can hold it, and as long as you're moving it, it stays in a ball.
No.
But as soon as you let it sit, it will flow through your hands. So.
I think we should go to the lab and do it.
If I had cornstarch, we would, but sorry. Anyway, the measure of how something flows, we have a special name for that. Viscosity. Viscosity. Okay. If something is viscous, if it has a high viscosity, it resists flowing. Okay. So things like syrup, things like honey, things like molasses. Okay. When you try and pour these things, you're waiting for a while as it slowly pours out. Okay. Now there are several factors that go into a liquid's viscosity. The first one is the attractive forces, the intermolecular forces between the particles. So think about it. If you have something that has a whole lot of interaction between the particles, okay, there's a lot of these forces between them. Well, those particles aren't necessarily going to want to move and tumble over each other, because that's what happens when you're pouring something. The particles are all mixing and sort of, like you said, tumbling over each other. But if they're really stuck together, they're going to resist that. They're going to resist that movement. But if they have less interactions between each other, then that is going to increase the viscosity, or decrease, sorry. It increases how well it can flow. The next one, particle size and shape. If you have little, well, let's think about sand. Okay, if you have little tiny pieces of sand, you can pour that out pretty well, right? It pours pretty smoothly. But if you have a bucket of rocks, okay, it doesn't necessarily pour as much as individual pieces sort of fall out. Okay? So smaller size particles are able to flow over each other a little bit better. And then it also has to do with the shape. Basically, if you have the shape of the molecule where it can get caught on another one, physically get caught, that also slows down how it's going to pour. Okay. And then this final one is temperature. If you have a very thick, viscous fluid, if you want it to pour faster, heat it up. When you add the kinetic energy, it allows these particles to move past each other a little bit easier because they have more kinetic energy. You can see this, with any foods, so like syrup and honey. If you will heat them, they will form much, much easier. The book also gives the example of like cooking with oil. Any of you, I don't know if any of you do a lot of cooking, but if you put a little bit of oil in the pan, it sort of pools together. But once you heat it, it really spreads out. Okay, you've increased that kinetic energy, which allows these molecules to move past each other a little bit easier. Okay. Now the next thing we want to talk about is something called surface tension. There's a lovely little picture on page 418 of a spider. Now this spider happens to be on water, but it's not underneath the water. Okay? It is just on top, but it's not floating. It's actually walking on top of the water. How does it do that? Well, as it turns out, the hydrogen bonding between the different molecules is keeping these molecules together. Okay? And it takes a certain amount of force to break those hydrogen bonds. Okay? When you push your hand through the surface of water, you have to use force to break those hydrogen bonds. Now, as it turns out, gravity interacting with your hand is enough to break those hydrogen bonds. But when you have something with a little bit less mass that has a weaker interaction with gravity, well, it can rest on top of the water. We can also, on Friday for you guys, we're going to do an activity with surface tension, which we'll talk a little bit more about on Friday. So yeah, that'll be Friday's activity. You guys have a few extra days in the A-Day section and the B-Day section, and so we'll build in a couple of extra things like that. So anyway, basically, the interaction between these water molecules is enough that something can rest on top of the surface. It's not like we said, floating, because floating, you break the surface, but then you come to an equilibrium. Surface tension, it's completely on top. Okay, it's not under the surface at all. And different liquids have different surface tensions. Okay? It all depends on the interaction between the molecules. Okay? This is also why, let's say, if you take a coin and start putting drops of water on it, okay, you can basically fill it up, and so that the water is bulging around. Okay, that's the surface tension. It's holding on to it. It's also why water forms drops, okay? Because the surface tension is holding everything together. Okay? Interesting, like for an astronaut, you take a rag that's full of water and squeeze it out, it all sort of just stays with the rag on the outside because of the surface tension. So maybe I'll find a video of that. I can show you an example, but it, you know, it's the surface tension making it so that it all stays together instead of just falling apart. So, it also mentions that there are specific chemicals that can interfere with these hydrogen bonds to make surface tension weaker. We call those surfactants. It also talks a little bit about these cohesion and adhesion. Basically, if you have water in a container, if you look closely around the outsides, it crawls up the sides a little bit. That's basically the interaction between the material that you have and the container. Okay. Different substances, I guess we'll say, will crawl up the side of the container more than others. Okay. Just depending on the interaction that they have. Okay. And that is liquids. Let's talk about solids now. Solids are, well, they're defined by, they have a specific volume that doesn't change, like liquids, but they also have a specific shape. If you were to take the a solid and change it from one container to another, it's going to retain its shape. Well, keeping with water, we could have ice. So if this was full of ice, okay, we could pour it into a different container, and all of those pieces of ice would retain their shape. Okay? Because they're solid, and that's what solids do. The reason for that is they have even stronger interactions between the molecules. Okay? Solids have the strongest interactions between them. That's why they don't flow and change their shape. Okay? In general, solids are more dense than liquids. There's one very, very important exception to this. Does anyone know what it is?
Jelly.
No. A solid that is less dense than its equivalent liquid. Water.
Oh, I was listening to that.
Trust yourself.
That sounded too obvious.
Yeah.
It doesn't have to be more complicated than it is.
I just want to look it up on Google.
That's why ice floats, because when it freezes and becomes solid, it's less dense. That's honestly a very, very good thing. Because if ice was more dense than water, well, what would happen in the oceans whenever ice would freeze, it would sink to the bottom.
Whoa.
And it would crush everything, and then it would stay frozen at the bottom, and yeah, it wouldn't be a good thing. So we're lucky that that ice is less dense and therefore floats. The fact is, though, most of the time, if you have the same substance in solid and liquid, the solid will be more dense and therefore would sink. Okay? So, anyway. Okay. Now, I'm just going to pause here and say the next little section has some complicated things in it. Okay. That being said, I'm not going to put a ton of emphasis on it, like on the exam. Okay. So get what you can, but if it doesn't make sense, don't stress over it. Okay. Because what we want to talk about are crystals. Now, a crystal, or a crystalline solid, okay, so it's a solid whose atoms, ions, or molecules are arranged in an orderly geometric structure. Okay. So basically, what we're saying is, in a crystal, the interactions between the molecules or the atoms or ions, whatever it is, it's predictable. We have a basic shape that repeats over and over and over and over. Right? Now that in and of itself isn't too complicated, but let's look at some of the different possibilities that we can have for these shapes. Now, the simplest repeating shape that you can find, we call it a unit cell. A unit cell. And then that unit cell repeats itself over and over and over. It gives us 7 examples on page 421. Okay. The simplest is the cubic. Okay, is cubic, and that really, the name speaks for itself. It's cubes. Okay, all of the sides in that unit cell have the same length, and they are all at 90-degree angles. Okay. But then things get a little bit more complicated. So we get tetragonal, and that is more of a rectangular prism. Okay. Specifically, a rectangular prism going up and down. Because if you have a rectangular prism going side to side, we call that orthorhombic. Okay. And that's one of the reasons why crystals can be a little bit not so straightforward, because you think, well, if you take the tetragonal and just do that to it, wouldn't it become orthorhombic? No. Okay, you can't just lay it on its side. There's more to it than that. Okay. Then they get really interesting down here at the bottom. Okay, we get the triclinic, where none of the sides are the same length and none of the angles are 90 degrees. Then we get the hexagonal, we get the rhombohedral, monoclinic. Those 7 are not all of the shapes. Okay. Number 1, there are variations on the cubic. We can see some of those in figure 19 on the previous page. But yeah, so basically what we're dealing with a crystal is you've got this unit cell, it's the basic shape, and we make that shape over and over and over to build this structure. So we also can break down the different types of crystalline solids. There is a lovely chart on page 422. Okay. If you have nothing but atoms in the crystal, we call it an atomic crystal. Okay. These crystals are not very strong. Part of the reason is because if you just have atoms, it means they have to have a full valence shell on their own without being an ion. And that just leaves group 18. And so they have pretty weak interactions with each other because they already have a full valence shell. They're happy. So yeah, we don't see too many of those. But the other ones we're going to see a little bit more common. So, molecular solids. Basically, we have individual molecules that are held together by these intermolecular forces, whether they are dispersion, dipole-dipole, or hydrogen bonding. I will take a moment. I think I told you that dispersion was almost always weakest. I realize that's not 100% true. It's not really going to affect anything on the test, but just, I don't want to lie to you. So often dispersion can, depending on the properties of the molecule, be stronger than dipole-dipole. It just depends. So, but it is still true that hydrogen bonding is one of the strongest interactions. So, okay. But yeah, so we get these interactions of the molecules in any of these different ways, and they form together, and they form this crystal structure. As it turns out, larger molecules are able to do this pretty darn well because if they're bigger, they have a lot more capability of having these interactions with each other. Okay? And it takes more kinetic energy to break them apart. Okay? One example of this would be sugar. when you measure out sugar, if you're baking a cake or whatever, those little individual pieces, those are sugar crystals. Okay? That sucrose has crystallized and formed those crystals. This group can have varying properties. Okay. None of them are super high melting points, but some of them can have relatively high melting points. They are typically fairly soft because, well, it's just these intermolecular forces that are holding them together. All right, the next on the list, covalent network solids. Covalent network solids, the crystals are held together by covalent bonds. We actually make covalent bonds around all of the individual atoms in this crystal. And that makes these very strong. Okay? Probably the most well-known example of a covalent network solid is a diamond. Okay? A diamond is just carbon. That's all it is. But what happens is you take the carbon and it's subjected to such high temperatures and pressures that these carbons form a covalent crystal. Now, carbon-carbon bonds are pretty strong. Right? It requires a fair amount of energy to break them. But when you have carbon, which is covalently bonded to 4 other carbons, and all of those carbons are covalently bonded to 4 other carbons, and you get this huge structure, and it's all one molecule. Okay? It's a giant molecule, but it's all one molecule. So if you have any diamond jewelry, that diamond is technically one molecule because all of those carbons have been covalently bonded together. Now, you probably won't hear anybody refer to it as a molecule because it's a covalent network solid, but really it's one molecule. They're all covalently bonded together. So that is why covalent network solids are, they're very strong, they're very hard, and they have very high melting points because, well, I mean, to make a diamond melt, you have to break covalent bonds, which isn't really making it melt, you are destroying it. So yeah. Then we get ionic solids. Okay, we've talked about ionic solids already. We talked about ionic bonding and how we said like you would get a positive sodium next to a negative chlorine, and it builds this big structure. Okay, that's an ionic solid. Okay, the interactions are just the positive and negative. And so, yeah. And then the metallic solids, once again, we also talked about this. Basically what you get is a bunch of the metal nuclei that are all together. And all of their electrons just sort of pool around them. Metals allow their electrons to move and jump from atom to atom. This is why they conduct electricity. But yeah, so All of those are different crystalline solids. And then the last one that we have, an amorphous solid. So amorphous basically means it's not a crystal. Okay. Amorphous is from the Greek. It means without shape. All right. What happens usually is we have something that's melted and it solidifies too quickly to make crystals. So all of the different molecules or whatever it is you're dealing with, they have come together and solidified so fast that they just sort of freeze where they are rather than making this crystal structure. Okay. Some examples: glass, rubber, a lot of different plastics are. Obsidian, if you're familiar with that, what that is. That's the rock that is on 424. So, but anyway, so that is the end of section 3. Any questions? All right then. I'm actually going to give you a break from homework today. So it's getting towards the end of the semester. There's a handful of you that have a couple missing assignments. I would work on those instead of doing homework for today. If you don't have any missing assignments, then you can do something else for the rest of class and you don't have homework due Friday.